Hello everybody, this is Pranav and in this video I'm going to brief about parallel in, parallel out shift register. So before starting off with the register, let me tell you about a flip-flop. So basically flip-flop is an electronic device which stores one bit of information or one bit of data. Flip-flop is a bistable device which means it either stores 1 or either stores 0. If we group n number of flip-flops together, we can store n bits of data. This application is used in registers. So, registers is a group of flip-flops that can store n bits of data. Now, let us understand a shift register. Consider this diagram of 4 flip-flops. Here each flip-flop's output is connected as input to the next flip-flop. At first clock cycle, when we provide the first input, it gets stored in D3. At second clock cycle, when we provide the second input, the first bit of data, which was stored in D3, comes as output from Q3 and gets stored in D2. At the same time, the second bit of data gets stored in D3. After 4 clock cycles, the first bit of data gets shifted from D3 to D0. Similarly, the second bit of data gets shifted from D3 to D1, third from D3 to D2, and the fourth bit of data is stored in D3, with all flip-flops storing one bit of data. This as a whole is known as a shift register. So, a shift register is a register in which the binary data can be stored and this data can be shifted to the left or to the right when signal is applied. In the previous diagram, we saw the data being shifted from left to the right because we consider the leftmost flip-flop as the most significant bit and the rightmost flip-flop as the least significant bit. According to its usage, the data can also be shifted from right to the left. The shift register is also a type of digital circuit using a cascade of flip-flops, which means a series of flip-flops where the output of one flip-flop is connected to the input of the next. They share a single clock signal which causes the stored data in the system to shift from one location to the next as explained. Here, for shift register, there are two types of inputs and two types of outputs. Serial in and parallel in are two types of inputs. Serial out and parallel out are two types of outputs. Let's understand each one at a time. Serial in means we give one bit of input at each time or each clock pulse. Serial out means we get output of one bit at a time or at each clock pulse. But in parallel in, we provide all bits of data in a single clock pulse at a time. Similarly, for parallel out, we get all bits of data from the register at a time in a single clock pulse. For serial in and serial out, there are two shifts, right shift and left shift. In right shift, we provide the data on the leftmost flip-flop and the shift occurs from left to right. However, in left shift, we provide the data from the right side of the register and it shifts from right to left of the register. Similarly, in parallel in and parallel out, we have rotate right and rotate left. In rotate right, we provide the data in the most significant bit flip-flop and it shifts from MSB, that is right, to left. And when it comes to the least significant bit, it again shifts to the most significant bit and this rotation continues. In rotate left, we provide the data in least significant bit and the shift occurs from right to left to the most significant bit. When it reaches the most significant bit, the data bit which goes again to the least significant bit and the rotation continues. As you can see, serial in means the data is shifted into the first flip-flop one bit at a time and the flip-flops cannot be loaded in parallel. This means that in serial in you can input one bit of data at a single clock pulse but you cannot give n bits of data at a single time. Serial out means the data can be only read out of the last flip-flop and the outputs from the other flip-flops are not connected to the terminals of the integrated circuit. Parallel in means that you can give the n bit of data at a single clock pulse at the same time, and parallel out means you can take the n bits of data as output together in a single clock pulse all at the same time simultaneously. So there are four types of registers. 1. is SISO, that is serial in, serial out. Second is SIPO, serial in, parallel out. Third is PISO, parallel in, serial out. And fourth is PIPO, parallel in and parallel out. For this video, we are only concerned with the fourth one, that is parallel in and parallel out. Now, let us understand parallel in, parallel out register. This diagram is a parallel in, parallel out register which stores n bits of data. It contains n number of flip-flops FF1, FF2 to FFn. B1, B2 to Bn are data inputs and Q1, Q2 to Qn are data outputs for the flip-flops. These flip-flops are triggered by a clock. Now, when we apply the clock signal, we provide the data inputs at place of B1, B2 to Bn at once simultaneously. These flip-flops store the data inputs and at the same time they fill in the slot of Q1, Q2 to Qn, which means they are ready to give the outputs whenever the clock signal is applied. So as to say that when we apply the second clock signal, we can receive the data inputs Q1, Q2 to Qn at once simultaneously. This is the functioning of a parallel in, parallel out register. In the previous figure of parallel in, parallel out register is capable of storing n bits of input data. Each flip-flop stores individual bit of data appearing as its input. That is, flip-flop 1 stores B1 appearing at D1. Similarly, flip-flop N stores Bn appearing at Dn when the first clock pulse is applied. At the same time, the bit stored in each individual flip-flop also appears at their respective output pins, which means when we apply the input bits at D1, D2 to Dn, the input similarly equally is stored in the output pins Q1, Q2 to Qn, which means when we put in the second clock signal, the data is already in the output pins Q1, Q2 to Qn, and when applied the signal, we get the output at once. This indicates that the data storage as well as data recovery will occur at a single clock pulse in, parallel out registers. The previous diagram was that of a simple parallel in, parallel out register. To convert that register into a shift register, we have to modify its circuit by adding a combinational circuit and a control line SHLD as shown in the given figure. When the SHLD line becomes low, all the A2 AND gates become high due to the presence of an inverter on the SHLD line. Also, when the SHLD line becomes low, all the A1 AND gates become inactive. The output of these A2 AND gates serve as the input to the OR gates O1 to ON-1. Similarly, the output of these OR gates serve as the input to the flip-flops FF2 to FFN with the exception of FF1. The input to FF1 comes directly from B1. When the first clock signal is applied, the input data from B1 to Bn is given to flip-flops FF1 to FFN. These inputs are stored in D1, D2 till Dn. At the same time, the output pins Q1, Q2 and Qn are filled with these inputs, which means at that time we have D1 is equal to Q1, D2 is equal to Q2 till Dn is equal to Qn. When the SHLD line becomes high, all the A2 AND gates become low due to this inverter and all the A1 AND gates become active. This causes a shift of data from one flip-flop to the succeeding flip-flop. Since this shift occurs from left to right, this diagram is that of a parallel in, parallel out right shift register. As said, when the SHLD line goes low, all the A2 AND gates of the circuit become active while A1 gates become inactive. Thus, the bits of the input data word appear as inputs to the A2 gates and are passed on to the OR gates as outputs, which are further loaded or stored into their respective flip-flops at the appearance of first leading edge of the clock. This also indicates all the bits of input data words are stored into the register components at the same clock signal. Also, at the same time, these bits appear at output pins of their respective flip-flops, yielding a parallel output data word at the same clock signal. Now, when the SHLD line is made high, A1 gates of the circuit becomes enabled and A2 gates get disabled. This causes output bit of each flip-flop to appear at output of the OR gate, which drives it to the very next flip-flop. That is, output of flip-flop 1 appears as output of the OR gate connected to D2, meaning Q2 equals output of O2 equals D3 and so on. At this stage, if the rising edge of the clock pulse appears, then Q1 appears at Q2 and Q2 appears at Q3 and so on. This operation is right shift of the data within the register by 1 bit. The diagram shown here is parallel in parallel out left shift register. The operation is same as the right shift register. The only difference here is that of the shift direction. The bit shift from right to the left direction. So now the application of parallel in parallel out shift register. One of the application of it is that of data transmission, transmitting the data from a source to a destination. Now consider the parallel data inputs as the source and parallel data outputs as the destination. Now at the first clock signal, we give 8 bits of data as input at parallel data inputs at once. This is converted to serial data. This is done because rather than using 8 wires, we can use 1 wire. It reduces the cost and material. So serial data output is then transmitted to the destination as serial data input, and from there serial data input is converted to parallel data output. The conversion from parallel data to serial data is done by a converter. Introducing time delay and sequence generator are examples of applications for serial in serial out data registers. So this was all about parallel in parallel out shift register. I hope you understood the concept well. Thank you.